This presentation is about a novel heat pump configuration for cold weather district heating. So this presentation is prepared by this one. I'm Wissam Rashid, and we prepared this presentation with Nitin Karwa from Honeywell, and the second part of this presentation will be presented by Mr. Lintu from Fortum. So the first part is use this. So yeah, Mr. Lintu from Fortum. So the first part is an introduction of the questions that we want to solve and a theoretical approach in order to understand what solution we can have. And the second part is, as I said, Mr. Lintu will explain experience of the end user and his point of view. So this presentation is about district heating, about cold weather district heating, where temperature is very low at winter condition. Which one is pointer? So I'm searching button. So at winter condition in cold weather, we can have temperature lower than minus 10 degrees C, and this temperature can be for more than 300 hours per year. And for district heating, there is this part is around 5% of the heat demand. So our focus will be on this part to see what is happening at these conditions. So this district heating, when we have low temperature, we have the profile of water delivered to district heating. It can go to 115 degrees C in winter time, and it is around 70 degrees C in summer time. And water coming back from the district heating is around 50-55 degrees C. So as you can see here, there is a challenge where we need a lot of capacity at low temperature, at low ambient temperature, and we need this heat that should be delivered at high temperature. So what solution we are using today? We can put a heat pump that can deliver heat or hot water at 90 degrees C, and then when we need water at higher temperature, we can put electrical boilers. So the question or the challenge is that at this point we have a high demand on electricity, high demand on the grid. The first, as I said, the first part, we will try to answer this question, how we can get rid of electrical boiler and use 100% heat pump. So that's why I will go through different configuration. So these are different configuration that can be used in order to deliver this high temperature. So the first one is the reference one, which is at 90 degrees C. The second one, where we let the refrigerant go to very close to the critical temperature or higher. And this will allow us to achieve 115 degrees C. The next three configurations are also interesting, and we try to analyze this configuration to see which one is the perfect one for this case. So this one is a double stage. We have double compression and double expansion. This one is the standard cascade, and this one what we call a partial cascade. So I am interested to explain the last one because it will be the most interesting, and we don't have all the time to explain all this configuration in this presentation. So this last configuration is a like cascade system, but we have additional heat exchanger here condenser. So when we are working at low water condition, the first stage here can deliver water up to 90 degrees C, and then at lower temperature, lower ambient temperature, when we need very high water temperature, we can run this high stage and deliver water. So as you can see, we have a different heat exchanger where we can make subcooling of the working fluid and heat the flow coming back from the district heating, heat it up progressively from 55 to 115 degrees C. Yeah, the challenge is around this high stage where we need compressors that can run at evaporating temperature quite high. So in order to make the modeling of this configuration, we try to analyze different option of compressor. Of course, these data are from compressor manufacturers. So, and this analysis lead us to decide that we need a very simple compressor model in order to make this comparison of this different configuration. Because there is a big impact on the pressure ratio, on compressor performance. Also, the speed of the compressor impacts the performance. So that's why, to make it easy, we take only one profile. We make extrapolation of an existing compressor in order to cover high pressure ratio when needed. And then we try to run all these configurations to see which one is the best and can fit for this to solve this technical problem. So here I go directly to the result. We have the scope for each configuration by using 1233 ZE as working fluid, or a combination of ZE and ZD when we have cascade or partial cascade. So as you can see here, shortly, partial cascade and supercritical gives the best scope. So if we want to go deeper on the result, you can see that in this graph, we can get rid of electrical boiler. We don't have all this electricity demand on the grid at very cold weather. So we can solve the problem by using this configuration. And of course, the best one with lowest electricity consumption are supercritical and partial cascade. For supercritical, there is a challenge. The challenge is that we need to go to very high pressure ratio. That means the efficiency of the compressor can go down, and also we have high pressure at the compressor level. So there is a challenge to find the best or a good compressor to be able to do this configuration. So that's why, here in this slide, we try also, first step was to compare different configuration with one set of refrigerant. And in this slide, we compare all the configuration with different set of refrigerant to understand the impact of the refrigerant on this configuration. So you can see that we have a trend where the partial cascade and supercritical gives the best scope, whatever is the refrigerant. And of course, there is some small difference depend on the refrigerant. And you can see that, HFO here, ZE and ZD combination are very good for partial and supercritical. So that's why, to go to the end, this configuration seemed to be the best that we can put in place. We try to also to do analysis of the cost of this partial cascade and to see what will be the impact if we have an A1, A2L or A3 refrigerant, and we focus our analysis on volumetric capacity and pressure ratio and the impact on the capex, and also we estimate an additional cost for A3 refrigerant. So A3 refrigerant, the cost can be different from case to case. We have an estimation around 15 to 50% higher cost. And for our calculation, we use 15% for A3, 6% for A2L. And by modeling of these assumptions and all these inputs, we find that there is a quite interesting advantage by using this partial cascade with ZE and ZD, where we can have here we compare versus different type of hydrocarbon, and we see that there is all the time additional cost when we want to use hydrocarbon, mainly because of the flammability and also because we are losing the capacity, and we need bigger system and bigger compressors. So now I will ask my Mr. Lento to.
All right. That's the software, yes. So, all right. So we wanted to do a economical analysis on where we could use these systems and in what kind of application. So we do a lot of waste heat recovery from data centers, and at the moment in the Nordics, there's about 7 terawatt hours of electricity consumption in data centers. There's a big boom growing up to 20 in the next 6 years. So we need better technical solutions to deal with more constraints on the electrical grid. And this is a basic configuration of what we do. We connect to the big data centers with heat pumps and with existing technology, raise temperature up to about 86 degrees. And when needed, we use an electrical boiler to prime it up. And this is what Wissam also told you about, that the constraints on the network comes when there's really cold weather. So we did a business case on a project that is already operating. How would this technology affect the existing project? The project is about 5 to 6 megawatt heat pump solution connected to 2 data centers recovering the waste heat. And then we have a 2.5 megawatt electrical boiler in this project. So how does this kind of solution look like? You have the heat recovery on the left side, 3.5 megawatts from the data centers. You have 2 heat pump modules and an additional electrical modules. And as you can see, it's a good working system, but it's quite complicated. We need a lot of different heat pumps to do this kind of district heating heat recovery. And of course, what should not be neglected is that we need a lot of electrical systems, and it has a big capex effect on these kind of projects. So we have transformers for every single unit, for the electrical boiler, the 2 heat pumps, and of course a lot of space needed for the process and electrical stuff and the switch gears and the control rooms. So let's talk a little bit about cost for the existing project. The heat pump modules are about 3.8 million. Then you add on an electrical boiler, 0.8 million euros. And then you put in the electrical distribution, which is 1.4 million. And this is, of course, a high industrial standard on the unit. So there's also some additional cost around that. But we come up to 6 million in this existing projects. So by utilizing this technological solution that Wissam is presenting, first of all, the heat pump will of course be a little bit more expensive. It's a little bit more complicated. It's a partial cascade system, but we get rid of the electrical boiler and we get rid of some of the electrical in e-house module investments that are needed. And of course there's some other additional costs down in small that we didn't include in these things. But of course, and then the big part, when you get rid of the electrical module and the electrical boiler, your seasonal performance of heat also becomes way better. So the conclusions from our side when we did a business case on how it would affect our existing solution is that the biggest upside comes from the cost savings on the infrastructure side. Less infrastructure, no electrical boilers and less electrical infrastructure, less construction costs, basically. Of course, we have a better seasonal performance, and that gives also a positive upside to the how we're affected by the electricity costs on the market. So if we have better efficiency, bigger cost changes on the electrical market won't affect us as much as if we had a lower COP, for example. So yeah, the conclusion is that of course the technology is a little bit more costly on the heat pump side, but the overall prices are way lower, and the total cost of ownership is way lower also. And of course, when we standardize these kind of projects, we also get cost solutions and lower costs. But yeah, from our point of view, this is a technical solution that should be taken seriously and tested. And that's something we're going to go forward with. So thank you from my side also.